Hi everybody, welcome back to Oscillations and Waves. Here's a short video where I want to talk about the Fourier trick. And I want to talk about this particular trick because it's something that's going to help us not just in this class but in many classes. Because as we talked about in class, the Fourier trick is about really trying to think about how to take information and break it up into different representations. So the big picture looks something like this. I have some system, right? And I have that system is described by a number of masses, say, or even a function or a string, or I just have some collection of particles or some even continuum. And I want to write that system, which will say x as a function of t. I want to write that system as a combination of all of the solutions to, say, an eigenvalue problem, right? So I have a complicated piece of information, or I have a set of complicated pieces of information, which make up how is this system going to evolve through time. And I want to take that and I want to break it up into, say, a sum over states that I understand, right? So in general, we've been talking about these as, say, the eigenstates of our equations of motion, right? These are the modes of a finite system. And by taking that information and saying, I'm going to break it up into these modes, I'm really saying how much of that system is oscillating at one frequency, plus how much of that system is oscillating at this other frequency, plus how much of that system is oscillating at this third frequency. So in a way, we're taking the information, which used to be about block 1, 2, 3, 4, all the way to n, and now I'm talking about it as mode 1, 2, 3, 4, all the way to n. Right? And of course, we have the same number of modes as we have boxes, because we're just rearranging the information from where is each box to what is each mode doing. And when we write it like that, we know that this coefficient here, which appears in front of my state, must look something like an oscillator, right? And so I can use any parameterization of solutions to the shoe that I want. For this discussion, I kind of like to use the transcendental parameterization. So I'll call it, I erased it by mistake. I'll call it a sub I cosine omega I t plus b sub I sine omega I t. I'm going to have to make a little bit more room here, but plus b sub I sine omega I t, right, times e sub I. And we know what the omega i's are because they're given to us by the frequency of each one of the modes. And I know what the e sub i's are because those are the eigenvalues of the modes. But of course, this picture here is actually bigger than this because I understand this notation in terms of having a system of blocks or having a certain number of beats on a string. But I really think about it as some complete system, right? I have some notion of how the entire system is doing. And that system is going to be broken up. So that's what the sum does, right? Broken up over states. And this thing in the middle here, this coefficient, is really the question of how much, right? How much of the system is in each one of those states? And of course, there are two unknowns when it comes to how much, because I need to know what is its position and what is its velocity, right? Each of the blocks had two pieces of information. Each of my parameterizations has two unknowns. And so there's an amplitude and a phase that I have to worry about when I think about how much of it is in each one of those states. Okay? But I'm always doing this. I'm always breaking it up this way. As sort of a teaser or something, or a way to think toward the future, I can actually do this in many different ways, right? So if instead rather than thinking about particular states or breaking up vectors, I can also think about this as breaking up functions into some coefficients times some set of basis functions, right? And so this idea of breaking up my information into modes, or breaking up information into different solutions, is something that's really going to be a theme for the next couple of weeks. And that's why it's worth thinking about this big picture. I want to take my time-dependent thing and I want to break it into some coefficients times my states. Now, of course, the Fourier trick is really about extracting those two coefficients as I've written them, AI and BI. And so when doing the Fourier trick, it's always the same sort of routine, but let me make sure that we've walked through it slowly. In doing the Fourier trick, I'm going to have to unpack that sum, right? I'm going to have to invert the sum in order to solve for the A's and B's. And in order to actually do that, I have to be careful that my basis, that is the modes, the states that I want to decompose my system onto, are actually properly orthonormal. That is, that when I take the dot product of any two of these states, I get 0 unless it's the same state, and then I get 1, right? That's what this Kronecker delta means, is that if it's going to be 1 if I equals j, and it's going to be 0 if I doesn't equal j. So in general, when I have a state, right? Let me call it let me call it x of t, and I say that it's a sum over I of a sub I cosine omega I t plus b sub I sine omega I t. Right, there's my big coefficient times e sub I. I have to do a dot product, right? I have to take the dot product of both sides of this expression with some arbitrary some arbitrary member of my basis. So let me take the dot product with let's say, generally we use something like e sub j, right? So e sub j dot x of t is going to be equal to the sum over I. Now, of course, this dot product doesn't care about that coefficient at all, right? AI cosine omega I t plus b sub I sine omega I t. And I'm left with just e sub j dot e sub I, right? Now, you can see why imposing this condition here, right? That if in order for me to really make this Fourier trick work, it's important that that my basis is orthonormal. So when I do that replacement and put in delta ji here, this delta function does something very special to my sum, right? It takes my sum and it says, sure, you have n terms in this sum, but almost every single one of those terms is going to be 0, except for the single term when j is equal to I, right? Because this Kronecker delta is almost always 0. It's almost always 0, except in the special case where one of the terms has I equal j, right? That is, of all of the different possible values of I, there's only one time when I equals j, and therefore my entire sum collapses to just that one term. And therefore I can rewrite the right-hand side of this as a sub j, after all, because I has to equal j, cosine omega jt plus b sub j sine omega jt. And that's equal to this dot product of e sub j x of t, right? And this looks like something that I know how to solve, right? This looks like the shoe, right? It looks like solutions to the shoe, because I can solve this, say, at t equals 0, right? And then I can figure out what the a sub j's are, or I can take the derivative of this whole thing and I can figure out what the b sub j's are. In fact, we're going to do that in just a second. Okay. Now, I'm doing all of this, of course, assuming that there is just a discrete set of states, right? I'm talking about, I'm so far only addressing the Fourier trick in the regime where my basis vectors are discrete, and therefore that when I'm taking my full problem, I'm really decomposing it onto a sum over states, right? Because I'm allowed to index those states by some index I, right? And that is an important thing for me to remember here. There will be cases where I don't have a discrete set of states, and that's when things get really exciting. But again, that's a different chapter. So in the sense, now let's expand that a little bit, because what we found is that E sub j x sub t is equal to a sub j cosine omega j t plus b sub j sine omega j t, right? But now we want to actually find out what those a's and b's are, right? And so we have to go from the full time dependent system to the time independent system. And in order to do that, I'm going to need both the positions, right? That's what this line means, because I'm taking the dot product of e sub j with x sub t. But I can also take the derivative of this, right? And I'll make that one in blue. So if I just take the derivative, the states don't have derivatives, they're just constant vectors. I have now v of t, because v is the derivative of x of t. The derivative of cosine is minus sine, so minus a sub j omega j sine omega j t, plus the derivative of sine is cosine, so b j omega j cosine omega j t, okay? And now, if I evaluate both of these at t equals 0, right? So this is the initial positions and the initial velocities. Then I can plug in t equals 0 on the right-hand side. Well, sine of t equals 0, I did not mean to erase that. I meant to cross it out. Sine of t equals 0, sine of 0 is 0, and so these two terms go away. And now I have simple expressions, right? And cosine of 0 is 1, and so that makes this even better. I can make this a 1, and I can make this a 1, right? Now I'm able to actually solve for what a sub j, and b sub j are. Let me do that quickly, and then we'll talk about it. So a sub j, well, that's just equal to e sub j dotted with the initial positions of all of the masses, or all of the blocks. And b sub j is equal to e sub j v evaluated at 0 divided by omega sub j. And of course, that omega sub j is important not just because it happens to be the right answer, but also because of units, right? So velocity and position have different units, and therefore the omega j helps me to translate between those two. And of course, this looks just so much like what we got when we were looking at the shoe, right? When we were trying to find out what are the a's and b's when I have just a single particle. Here, I'm saying, what are the a's and b's for that particular mode j, right? And so if I know what my initial positions are, and I know what my initial velocities are, then I can find out what are all of the a sub j's and what are all of the b sub j's, right? There's a number of calculations in here, because j goes from 1 to n, and so I have n a's and I have n b's, but I can use these two formulas to really quickly come up with what those are. So I thought I would do just a quick example, because it's kind of nice to see the math, although we have a Mathematica document that we used in class that does this for the sort of generalized case, right? And we saw those great movies for that. But if I want to find out what are the a's and b's, well, first I need a set of initial conditions. So I'm going to just make up some. So we'll say that x naught. Let's keep the first. let's actually keep it at equilibrium at the first at t equals 0. So neither of the blocks are displaced, but I can make it so my initial velocity is kind of cool. I'll make it so that the one on the left is moving to the right with, say, 1 unit of speed. I should be careful here. I have all of my units in this expression, so I'll talk about 1 meter per second, and I'll have the one on the right moving backwards at 1 meter per second. Okay. Actually, this might be too easy because I can foreshadow where this is going to go. So let me make this one go at -2 meters per second. Okay. So the system, which is described in the book, you can look at equation 5.9. I have either 2 masses connected by 3 springs, or I have 2 beads on a string, and I have 2 states then associated with that because I only have 2 masses. And therefore I have 2 initial conditions. Both of the masses are at equilibrium, and I have 2 initial velocities. The left block is moving to the right at 1 meter per second, and the right block is moving to the left at 1 meter per second. So I have 4 different dot products that I have to do, right? I have to figure out, well, what is A1, B1, A2, and B2. So I know that A1 is E1 dotted with X0, and I know that B1 is equal to E1 dotted with V0. Now, the way I've written it, since x0 is 0, well, that's going to be 0, right? Because when I do that dot product out, I don't have to worry about that product having anything. On the other hand, this one is not going to be 0, right? So I have the bra version of E1, which is 1 over the square root of 2, 1, 1. And I'm going to dot that with 1, 1 meters per second. Okay, oh, I almost forgot about the over omega 1, right? And then I'm going to do 1 minus 2 meters per second. And then I have to divide that by omega 1, which is the square root of ml over 6t, right? And this dot product isn't hard to do. 1 times 1 is 1, minus 2 is minus 1. There's a square root 2, so that makes that a 12. So it's minus 1, let's see, ml over 12t meters per second. Okay, and I'm going to assume that all of the algebra worked out there. Now I'm going to do the I'm going to do the other 2 a little bit faster, right? So I know that A2, which is E2 dotted with x0, that's also going to be 0, and that B2 is going to be E2 V0 over omega 2, which is 1 over the square root of 2. E2 is 1 minus 1, 1 minus 2. Oh, that's going to be fun to do. Meters per second times ml over 6t. Okay, and that is going to give me, I just have to, so 1 times 1 is 1, minus 1 times minus 2 is minus, is 2, so that's 1 plus 2 is 3, 3 squared is 9, so I have in my square root, I have, let's see, 9 over 12, that probably can be simplified, but I'm not going to worry about it, times 6t meters per second. Okay, and so once I have all of my coefficients now, I know what's interesting is that both modes exist, right? I've excited both of these modes. They have different numbers associated with them, but of course the second mode is bigger, right? That is, its amplitude is larger. It's the square root of 9 over 12, not the square root of 1 over 12. So it's actually 3 times bigger, right? So I have more of the second mode excited than the first mode. But I can plug those back in if I wanted to, right? And I could say then that the full solution, x of t, which is going to be the sum, right? Which is the sum over I of AI cosine omega I t plus bi sine omega I t times e sub I, right? I can plug in these expressions. Both of those go away. So I can do one more line of algebra, which gets me to the point where x of t is equal to just the b1 sine omega 1 t e1 plus b2 cosine omega 2 t e2. And therefore, I now could plug all of the things in, but you can see that the amplitude of B1 tells me how much of it is in that first mode. The amplitude of B2 tells me how much of it is in that second mode. And then when I put it all together, I get just one beautiful vector that helps me to reconstruct x as a function of t, but gives me the information about how much is in each mode. Okay? And that's what the Fourier trick does. It allows us to solve for those coefficients. And by in having those coefficients, I'm able to figure out what the system is going to look like as a function of time. Okay, so things to remember. First, you need a good basis in order to do this. You have to know what the dot product of two different states are, and it's always better if that basis is normalized so that the dot product of any two states is 0, except if they're the same, and then it's 1. And of course, it never hurts to do the Fourier trick completely. Doing this dot product every time you need to solve for the coefficients, it takes like 2 more lines of algebra. And when you have those 2 lines of algebra, it helps you to remember why you're doing what you're doing, right? I take my system, I decompose it onto states, and then I find those coefficients so that way I can reconstruct the system as a function of time. Okay? And this is really an example of what we call an initial value problem. Right? I know how each state is going to evolve. And so if I take my initial conditions and I break it up into how much is in each state, I can then reconstruct the whole state as a function of time. All right. Good luck, and I'll see you shortly.